In this video, we'll look at tree diagrams and their use in representing sample spaces. A tree diagram is a visual representation of a sample space. Each outcome is represented as a branch. So on the tree diagram shown to the right, you can see that each outcome is either a head or a tail for flipping a coin. The probability of the outcome or event is placed above each branch. So as you can see, the probability of getting a head is 1/2 and the probability of getting a tail is 1/2 for a fair coin when it's flipped. Each stage of a multi-stage experiment is another set of branches. So you can see stage 1 is flipping the first coin, and then stage 2 is flipping the second coin, and stage 3 would be flipping the third coin or the same coin 3 times in a row. Tree diagrams are useful to represent sample spaces of multi-staged experiments containing 2 or more stages. The main power is being able to represent many stages in a row, so you could have 4, 5, 6, and it could keep going on forever if you wanted to. The use of tree diagrams is limited when there are too many outcomes to represent. So if there needs to be hundreds of branches to be able to show all the possible events or outcomes, it would be very messy to use a tree diagram in those sorts of situations. Tables and grids offer an alternative when you have more outcomes, but you'd be restricted to only 2 stages in an experiment, like rolling 2 dice is suited to tables and grids. When setting up a tree diagram, each set of branches is a stage. Each branch represents an outcome in a single stage. So for the first stage, you can have a heads or a tails. Following getting a heads, in stage 2, you could get a heads or a tails. Or if you follow on from a tail, you could get a head or a tail. And likewise for stage 3, the same outcomes present themselves in the third stage of the experiment. So if we trace along the first or the highest set of branches, you have head leading to head leading to head. So overall the event is getting 3 heads in a row. If we were to trace out another set of branches, you could get a head, a tail, and a tail, which would give you head, tail, tail as your event. The probability of the outcomes is placed alongside each of the branches. So again, the probability of getting a head or a tail is 1/2, so they accompany each of the branches in this tree. To determine the probability, we have particular rules we use for tree diagrams. So what we do is we multiply along the branches. So if we have a look at the blue path that we've traced out through our tree, we would multiply 1/2 by 1/2 by 1/2 to get the probability is 1/2 times 1/2 times 1/2, which is 1/8. We can also add probabilities of each of the events to produce another event or a new event. And lastly, we need to remember that the sum of all of the probabilities for all events must equal 1. So down here you can see the total equals 1, which is found by adding up the 8 events here, which all have a probability of 1/8. So we're going to consider the sample space when 3 coins are flipped. The tree diagram for this is shown. For part A, what is the probability of obtaining all heads? So all heads follows this set of outcomes. So that's the event all heads, and the probability for that is 1/2 times 1/2 times 1/2, which is 1/8. Therefore, the probability of head, head, head is equal to 1/8. Next, we want to look at what is the probability of obtaining no heads. So if we obtain no heads, we obtain 3 tails. So that is here, here, and here. So we look at this entry on the tree diagram. So the probability of tail, tail, tail is equal to 1/8. Next up, we want to look at the probability of obtaining exactly 1 head. Obtaining 1 head exactly was this series of branches, this series of branches, and this series of branches. So again, using our structure of the tree, when we go between branches, we add them. So we have 1/8 plus 1/8 plus 1/8, which gives 3/8, which is the probability of obtaining exactly 1 head. Next, we want to look at what is the probability of obtaining 1 or more heads. So we could go through and we could highlight all of the outcomes that have 1 or more heads in them, Or we can use the complementary rule of probability to say that that would be equal to 1 minus the probability of obtaining no heads or 3 tails. So that would be 1 minus, and we found the probability of 3 tails in part B, which was 1 on 8. So that means the probability of obtaining at least 1 or more heads is 7 over 8. So after this video, you should be able to know when to select tree diagrams to represent sample spaces. You should be able to use tree diagrams to visually represent sample spaces and events. You should be able to use tree diagrams to determine the probability of events occurring. And you should also understand the limitations of a tree diagram and alternatives to get around this.